All right, and today we're going to talk about the end behavior of graphs, and we'll talk a little bit more about zeros of polynomials and also the multiplicity. Okay, now as far as the end behavior of graphs are concerned, we're mainly concentrating on the extreme parts of a graph, the leftmost parts of a graph, and the rightmost parts of a graph. And we're going to split this up into basically two categories. You have, as far as degrees are concerned, you have even functions and odd functions. And I'm going to go through that real quick. Okay, and even function. Okay, even functions are symmetric with respect to the y-axis. So what that means is if you were to take a graph, and for example, we'll use a parabola. Y is equal to x cubed. Excuse me, y is equal to x squared. Right? And if you were to graph y is equal to x squared reform parabola, this parabola is an even function, which means it's symmetric with respect to the y-axis, meaning that we can fold this graph unto itself about the y-axis. Okay, if we were to take this graph and fold it vertically on the y-axis, the graph would overlap itself. Another thing about even functions, and this is if we're talking about a function, not necessarily a graph, if all the exponents in a polynomial are even, then we have an even function. Okay, so here's an example. Okay, y is equal to x to the fourth plus x squared. Right? That would be an example of an even function because all of the exponents are even numbers. Now we're going to talk about odd functions. And odd functions are symmetric with respect to the origin. Okay. So not necessarily to the x-axis. So notice that the even functions are symmetric with respect to the y-axis. Odd functions are symmetric with respect to the origin. Symmetry with respect to the origin simply means it's symmetric by both the x and the y-axis. So an example of an odd function is y is equal to x cubed. Right, if you were to graph y is equal to x cubed, the graph will look as such. Right, so y equals to x cubed is symmetric with respect to the origin. All right, so that's if we're looking at a graph. if you're looking at a function, if all the exponents in a polynomial are odd, and then you have an odd function. So if all the exponents in a polynomial are odd, then you would have an odd function. So here's an example. Y is equal to x to the 5th power minus 2x cubed. All right, that would be an odd function because if we look at all of the powers for x, they're all odd numbers. 5 is an odd number, 3 is an odd number. So if I were to ask a question, so odd, even, or neither. So let's say we have y is equal to x to the 5th minus 3x cubed plus 2x squared minus 9. Right? Is this odd, even, or neither? Well, in order to determine that, you just simply look at all the exponents. If all of the exponents are even, it's an even function. If all of the exponent is odd, it's an odd function. But if you have a mix of even and odd exponents, it's neither. All right, so looking at the first term in the polynomial x to the 5th, it has a degree of 5, which is an odd number. The second term in that polynomial, negative 3x cubed, has a degree of 3, right? That's an odd. But if we look at the third term, 2x squared, that 2 is an even number, so this would be neither odd nor even. Okay, now in a previous, I think it was in the last class, we talked about a leading coefficient. And a leading coefficient, well, we talked about a dominating term, and we talked about a leading coefficient, right? So the dominating term, right, if we were to take this one, for example, the y is equal to x to the 4 plus x squared. The dominating term would be that term with the largest power. So for x to the 4 plus x squared, the dominating term is x to the 4. The dominating term has a leading coefficient. All right, so that leading coefficient is an understood 1, right, positive 1. If we look at this example, y is equal to x to the 5th minus 2x cubed, the dominating term is x to the 5th, and its leading coefficient is positive 1. If we look at the last polynomial, x to the 5th minus 3x cubed plus 2x squared minus 9, the denominating term is x to the 5th, and it also has a leading coefficient of 1. Now, I point that out because when we talk about the end behavior of graphs, we're going to concentrate on that dominating term. We're going to concentrate on the leading coefficient, right, whether it's positive or negative. We're also going to concentrate on the degree or the exponent of that dominating term. Okay, so this is the end behavior of graphs. All right, so first we're going to look at the even side of things. So let's say we have f of x is equal to a times x to the nth power. Okay, so what a times x to the nth power, that represents the dominating term of our polynomial. if the leading coefficient of the dominating term is positive, all right, so a greater than 0 just alludes to the fact that the leading coefficient is positive. And if the exponent is odd, excuse me, if the exponent is even, I'm going to write this out a little bit better. Oops. Okay, so I'm going to split this up. So we have a is greater than 0 and n is even. So remember that a is just the leading coefficient and n is our exponent. If we have both of these conditions, then our graph is going to rise to the right and it's going to rise to the left. And I'm going to give an example of what I'm talking about in a second. And on the flip side, if our leading coefficient is negative, so a less than 0 is negative. And if n is still even, then our graph is going to fall to the left and fall to the right. All right, so I'm going to use the graphing calculator. All right, and we're going to take a look at some graphs. So I'm going to use y is equal to x squared, right? So if we graph y is equal to x squared, I'm just going to use zoom 6. Notice that fits this first condition over here. Right, the leading coefficient is positive. It's an understood positive 1. N, which is the exponent, is even. So notice this graph rises to the left and it rises to the right. Now, the reason I write these little squiggly lines in the middle is because it may hit the x-axis more than one time. All right. So I'm going to look at another function. I'm going to put in x raised to the 4th power. So notice it still holds the same conditions. The leading coefficient is positive and my exponent is even. So when I graph it, it should rise to the left and rise to the right. That's true for any polynomial whose leading coefficient is positive and the exponent is even. Right, so one last example, I'm going to put in 6x raised to the 6th power. All right, keep in mind 6 is still a positive number. My exponent is still even. So that graph rises to the left and to the right. Now, if we look at the second setup, if a is negative, if the leading coefficient is negative, then our graph should fall to the left and it should fall to the right. All right, so I'm going to put in negative x squared, and I'm going to graph, and notice it falls to the left and it falls to the right. Now we're going to take a look at odd functions. And we're going to break this up in a similar fashion. So if A is greater than 0, right, that means that the leading coefficient is positive. And if N is odd, then our graph looks something like this. Right, it should fall to the left and rise to the right. And if A is negative, and if N is odd, then it's going to rise to the left and fall to the right. All right, so we're going to take a look at an example, and we're going to graph x cubed. So I'm going to go to y equals, and I'm going to clear that out. I'm going to put in x raised to the third power and graph. So notice when we graph y is equal to positive x cubed, right, it fits this first condition. The leading coefficient is positive, N is odd, so it falls to the left and it rises to the right. Let's say if I were to put in x raised to the fifth power, right, it should follow that same pattern. It should fall to the left and it should rise to the right. And in order to see the other setup, I'm going to put in negative x cubed. So negative x raised to the third power, and this graph should rise to the left and it falls to the right. Okay. So this is the end behavior of graphs. Okay, and we'll see why that's important. Let's see, I'll find a question that deals with that. Okay, here is one that is similar to number 9. Y is equal to negative 2x cubed plus 16x. All right, and we're asked a couple of things. First off, we're asked to determine the end behavior. Okay. All right, so in order to determine the end behavior, we're going to look at the dominating term, which is negative 2x cubed. Oh. All right, and we see that the leading coefficient is negative, the exponent is odd. So we look back to our setup, right? I believe that would fit this setup. The leading coefficient is negative, the exponent is odd. So that graph should rise to the left and fall to the right. So rise to the left and fall to the right. Okay, so that's the end behavior part of it. The next thing we're asked to do is find all X-intercepts. Right, so keep in mind the X-intercepts are the same things as the solution. It's the same thing as the zeros. All right, so we're going to solve it. So I'm going to take negative 2x cubed plus 16x, and I'm going to set that equal to 0. So now we talked about a couple of methods to solve higher order equations. We could use the zero function on the calculator, so that's still an option. I believe the last time we used synthetic division, right, we can find all the possible rational zeros. You could also factor and use a zero factor property, okay, which I didn't show the last time because none of those polynomials were factorable. Okay. All right, so in order to solve this one, I'm going to factor out the greatest common factor, which in this case would be negative 2x So once I factor out a negative 2x, on the inside of the parentheses, I'm left with x squared minus 8. Right? Because negative 2x times x squared, that's negative 2x cubed. Negative 2x times negative 8 is positive 16x. All right, so we have factored. The next thing I'm going to do is use the zero factor property. Right, so I'm going to take each factor and set each factor equal to 0. So I'm going to take negative 2x, I'm going to set that equal to 0. I'm going to take x squared minus 8, set that equal to 0. And now I'm going to solve each one. So for negative 2x equal to 0, I'm going to divide both sides by negative 2. So I have one of my solutions as x equals to 0. And now we're going to solve the other equation, x squared minus 8. So in order to solve x squared minus 8, notice that I can't factor x squared minus 8, but I could use the square root property. Right, so using the square root property, we have to isolate the square. So I'm going to add 8 to both sides. So we have x squared is equal to 8. And we're going to take the square root of both sides. So if we take the square root of the left-hand side, the square root and the square cancels. If we take the square root of the right-hand side, notice by using that square root property, we must sprout a plus or minus. So keep in mind that all of the radicals must be simplified. So I'm going to rewrite the square root of 8 as the square root of 4 times the square root of 2. Right? We talked about the product rule for radicals. Any two numbers you can multiply to get the radicand. You can separate it out. So I could use 1 times 8, but the square root of 1, it's a perfect square, but that kind of puts us where we're starting with. So I'm using 4 times 2, which is 8. Notice that 4 is a perfect square. So the square root of 4 is perfectly 2, so we have 2 square root of 2. So our three solutions are 0, negative 2 square root of 2, and positive 2 square root of 2. So those would be our X-intercepts. And these are the 3 points where our graph would cross the X-axis. All right, and then they asked for some other questions. So that was B. And then this is what C says. X-intercepts where the graph crosses the X-axis. And then there's another part of C that wants us to answer where the X-intercepts or the X-intercept where the graph touches the X-axis and it turns. Okay. All right, so I'm going to kind of explain these two. So for the first part, it says where the X-intercepts, where they cross the X-axis. So I'm going to graph that equation just to get a visual of what's going on. So negative 2x to the third power plus 16x. All right, so if we look at the graph, so over here, I believe I would have negative 2 square root of 2. So notice that for this X-intercept, it completely crosses the X-axis. For this second intercept, 0, notice that it completely crosses the X-intercept. And for positive 2 square root of 2, notice that it completely crosses. The second part of this, problem says where it touches and turns. Right. So this is just an example of touch and turn. right? So let's just say we have this. Okay. All right, so this point would be an X-intercept, right? And it would cross. Okay. This point, right, would be an X-intercept, right, because it actually touches the X-axis, but it doesn't cross through. It actually turns around where it touches and turns. So notice for our particular graph, notice that we don't have anything that touches and bounces off. Okay, so that's what a visual for what the second part of that question wants. So in order to answer the first part, I would just put in -2 square root of 2, 0, and 2 square root of 2. Because they completely cross the x-axis. For the second part of this equation, we have it doesn't happen, so we're going to put in D dot N dot E, and that's short for it does not exist. Okay, there are no X-intercepts where it touches and turns. And then the last part asks for the Y-intercept. So this will be part D. The Y-intercept. Okay. So how do you find a Y-intercept? To find the Y-intercept, we let x equal 0 and solve for y. So we have y is equal to -2x cubed plus 16x. I'm going to let x equal to 0. So in that equation, wherever I see an x, I'm going to substitute it with 0. So we have y is equal to -2 times x, which I'm substituting for 0 raised to the third power, plus 16 times x, which again I'm substituting for 0 and raising to the third power. So once we simplify, we have y equals 0. So the y-intercept is 0. All right, so in order to find the x-intercept, you let y equal to 0 and solve it for x, which is what we did for the first part, right? We just let y equal to 0. We just set it equal to 0. We solve for x. In order to find the y-intercept, we let x equal to 0 and solve for y. All right, now I want to look at some graphs. And this one is similar to number 4. So we talked about zeros and multiplicity, right? Given a function and given zeros. Here we're actually going to take a graph, and from the graph we're going to pull out the zeros and we're going to pull out the multiplicity. All right, so this one will be similar to number 3. So the directions tell us to use the graph to identify zeros and multiplicity. Okay, and when you're putting them in, you have to be specific. It wants us to order your zeros from smallest to largest, or from least to greatest. Okay, and I'm going to try to reconstruct this. All right, so I'll give you a second to reconstruct that. So I didn't draw out an elaborate graph or anything. I just sort of labeled out the X-intercept points. All right. So first off, just keep in mind that the X-intercept is the same thing as a 0. So the X-intercept is the point where the graph crosses the x-axis. So we have an X-intercept point here at -1. We have a 0 at 2. Right, +2 is where it hits the x-axis. We have a 0 at 3 and a 0 at 4. And then for the multiplicity, you just want to keep in mind here that if it crosses the x-axis, the multiplicity is 1. But if it bounces and turns, the multiplicity is 2. And we'll see one that actually bounces and turns in a second. So as we take a look at this one, notice that at -1, it crosses through nicely, so the multiplicity is 1. At +2, it crosses through nicely, so the multiplicity is 1. And the same thing happens for 3 and 4. All right. However, if we take a look at number 4, all right, so the directions are the same. Use the graph to identify the zeros of multiplicity, and we're going to order from the greatest to the least. So this is -3, -2, 1. Okay, that's supposed to be touching me. All right, so we're going to do the same thing. All right. So I'm going to just write out the chart. We have the zeros on one side, the multiplicity on the other. So the zeros are -3, -2, and 1. Notice that at the 0, -3, it crosses through nicely, so the multiplicity is 1. However, at -2, notice that it bounces and it turns around. So we would have a multiplicity of 2. All right, for any bounce and turn, the multiplicity is 2. And then for +1, it crosses through nicely, so we have a multiplicity of 1. Now, if you had to find a degree for this polynomial, right, so notice that it falls to the left, it falls to the right. So that means that the power should be an odd number, right, either 2, 4, 6, or 8. So for my zeros, notice that my multiplicity, they add up to 4. Right, so this would actually be some type of 4th degree equation. Okay, and we will look at some more graphs. And this is similar to number 12. And they actually want us to pick a graph. Okay, pick the graph of the following. So we have f of x is equal to x times x plus 3 squared. And I'm not actually going to draw all of the graphs. Okay, but we're going to be able to pull some things out about the equation itself. Okay, and we're going to make a rough sketch of the graph. All right, so the first thing I'm going to do is we're going to find the zeros. So I have x, and we have x plus 3. Okay. So notice I didn't write x plus 3 quantity square. Okay, we're gonna put the multiplicity in separate. All right, so I'm going to set each factor equal to 0. So we have x equal to 0. We have x equal to, and x plus 3 equal to 0. If we solve for x, we have x equal to -3. So if I were to graph, I have -3. And I have 0. Right. We're also going to take into the end behavior of graphs. Okay. So notice from the function we have x times the quantity x plus 3 quantity square. Which means that this is actually a cubic equation. And I am going to write that out. X times x plus 3 quantity square. So if I were to take x plus 3 times itself, x plus 3, that would be x squared plus 6x plus 9. And then if I distribute my x, I'm going to have x cubed plus 6x squared plus 9x. Now, this is not really required for this problem, but I wanted to just point out this. This is a cubic equation, right? So if we take a look at the end behavior, the leading coefficient is positive. The exponent is odd, so that means that it should fall to the left and it should rise to the right. So taking a look at all of the graphs, they all fall to the left, they all rise to the right. Okay. I know that I have the zeros and I'm just going to go up. And a multiplicity. Right, so we have 2 zeros, -3, and we have 0. So if I pull out my multiplicity just based on my function, -3 has a multiplicity of 2. Right, so anything that has a multiplicity of 2 is going to hit the x-axis and bounce off. 0 has a multiplicity of 1 because the power on x is 1. So this graph should look something like this. It should fall to the left, right? It should hit -3, and since -3 has a multiplicity of 2, it's going to bounce off -3, and then it's going to cross through at 0. So the graph for this function should look something similar to this. Now, for these graphing type problems, I know that might have been a long-winded explanation. You can simply put it in your calculator and you can graph it. Okay, so if you were to put x times a quantity x squared, no, x times a quantity x plus 3 quantity squared, and if you were to graph, I'm going to do that here. All right, notice that's what the graph will look like. Okay. All right, and we will take a look at the very last problem. Okay, and the directions tell us to, it just says consider the function P of X is equal to X minus 8 times X plus 3. Okay, and for part A, we're asked to find the Y-intercept. All right, so from what we've seen earlier, in order to find the Y-intercept, we're just going to let X equal to 0 and solve for Y. So let me just write that here. Let X equal 0 and solve for Y. So we have Y is equal to X minus 8 times X plus 3. And we're going to let X equal to 0. So wherever I see an X, I'm going to substitute a 0. So Y is equal to 0 minus 8 times 0 plus 3. So 0 minus 8 is negative 8. Notice I'm still keeping my parentheses. 0 plus 3 is 3. Negative 8 times 3 is 24. All right, so the Y-intercept is negative 24. Now, if you want to put that in as an ordered pair, keep in mind that we set X equal to 0. So as an ordered pair, it would be 0, comma, negative 24, which is what they want. They want it as an ordered pair. Okay, so that's the first part of it. Now it asks for the X-intercept. So B wants us to find the X-intercept. Okay, my battery's running out. Okay, so finding the X-intercept, that's just like solving it, right? So in order to solve it, we're going to set it equal to 0. X minus 8 times X plus 3 is equal to 0. I'm going to use a 0 factor property. X minus 8 equal to 0, X plus 3 equal to 0. And we're going to solve. So X minus 8 equal to 0. I'm going to add 8 to both sides. So X equal to 8. Y plus 3 equals to 0. I'm going to subtract 3 from both sides. So X equal to negative 3. We must answer these as ordered pairs. Okay. So remember, when you find the X-intercept, you inadvertently let Y equal to 0 and solve for X. All right, so for each one of these ordered pair points, I'm simply going to let Y equal to 0. So for the X-intercept X equal to 8, that's actually the point 8, comma 0. And for X equal to negative 3, that's actually the point negative 3, comma 0.